Good evening to all. In this video we are going to perform the bit bank IIC on the FMD chip. Okay. So the cause why we are going for this arrangement bit bank for the ICC. When I look the selection chart for the FMD chip, there are lots of chips in this series where we don't have I2C, then SPI and UART. So if we are using the low cost chip from the FMD, then we need this I2C and SPI UART either by on a hardware base, or we have to develop these software based I2C, SPI and UART. So today we are focusing the I2C as a soft implementation for those chips that doesn't have any I2C. Okay. For the reference, I just go through what the I2C for 2402. It is a memory chip. So it has only two signals for consideration of the data transaction: clock and the data. There is some conditions are there: start condition, stop condition. When SCL is 1 and the SDA goes to low, this is called start condition, and the reverse is happening when SDA goes high. When at condition clock is high, then it is called as stop condition. And to send the data on these two lines, actually in one line on SDA, we have to, at the low of that clock, we can change the data on the SDA, and we have to place the clock on the SCL. Okay, in this way we can send the data. There is a standard format for the each chip. You have to go through the data sheet itself. So there is one acknowledgement bit at the last of transaction, that is the 9th bit. So on the basis of that acknowledgement bit, we are able to know whether the read or write transaction is successful or not. Okay. So generally at lower speed and very confined way, we can also ignore this status bit. We assume that it is a correct transaction. Anyway, for the 2402 memory chip, there is a control byte format, and this is called a slave address, and this A0, A1, A2 is a physical pin of the chip. You can connected almost 8 2402 on same bus line. So 1010 address, and physically we can differentiate between chips using these physical pins. So the format is simple. We start with the start condition. We have to send the control byte format. Then we need to define whether we are going for read or write, and the last one is acknowledgement. So it is very simple. I hope you are already familiar with these things. So to write the byte, we have to, as I told, we have to start with the start, then send the control word, as you see 1010, then 3 bits for the physical, and we are going to write. So 8 bit is low, and the 9th bit is the acknowledgement. We have to place the address, and then we can able to send the data. And if you want to send the consecutive writes, then automatically inside that chip there is a pointer. It will automatically write the data on the consecutive next addresses. Okay. Similarly, there will be some reading process as well. So whenever there is whatever the case there, when we are send some data for the write, there will be some address. So when we, after that, if we are going to read, then whatever that last address, we actually read the data from that particular address. Okay, so if you are going for the consecutive as well, you can go for the consecutive, and even though you can go for the random access also. Once we are going for the writing process, okay, then we have to place the address, then we have to restart the process, then we are going for the reading control write, and then we can read. This way we can read the random data from the random address location data from the specified addresses. So in this same way we can have the sequential reads as we seen in the write process. So for the bit banging, obviously we need this start condition, bit arrangements, then acknowledgement, then stop condition. These are the subroutines that we are going to see. Okay, so I choose the 131 FTM chip 62F13. It can be 8-bit. It can be. This is a datasheet for 13 series. It can be 8-bit, 10-bit pins, or 14, 16, 20 pins. But it doesn't have any I2C hardware arrangement in this chip. Okay, so I prefer 131 here for the example. So I connect the clock at PA4 and SDA pin at PA2. So I just include the required header files, then define the port pins as a SCL and SDA. Also, when we are sending the data, that SDA should be at output side, means we have to define as output, so we make the trias as a 0. When we are trying to read the acknowledgement or read the data from the chip, so we need to make this SDA as an input. So in this way we can make SDA as out or in, okay, by using the trias. So this is a simple microsecond delay, this is a millisecond delay, this is a second delay. So at the power initial, these are the very standard values that we seen in earlier video FTM chip. Trias is obvious, either we have to place as 0 because we need both pins as output. So we are also not touching anything here. At start condition, we have to keep the first two lines high, then we make the SDA first as a 0, then SCL. So this is the start condition. We are going for bit by bit. This is the stop condition. This is a IIC wait acknowledgement. We are waiting up to the 250 micro. If it is still not there, we are returning as failure. Acknowledgement. Okay. So this is a no acknowledgement bit routine. To send the byte, we have to make the SDA as output line. Then we start with a looping arrangement. Okay, one by one in the text TXD argument, we are shifting the 1 bit and making it clock 1 and 0 after some 5 microsecond delay. So in this way we can send the data out by bit. Also we can read the data. In that case we make the SDA as an input, and we can place a clock, whatever the data inside this on the SDA pin, we gradually take that as an input. Okay, so again we have to place a no acknowledgement while reading the data. So in the read process, obvious, there will start, we have to place the address of the chip, that is A0. Okay, So then we have to read the acknowledgement. If it is not there, we have to looping back. Okay, and once we place the addresses, we have to restart the process to read from the particular address. Okay, in that case we have to place A1 because we are reading that LSB bit of control word becomes 1. Okay, so at last we have to stop. Write also is the same thing. In that case, this is a control address, control word, then address we have to place the data like that. So in main I just put a read the data from the 12H location, and we just complement that and put on the 13H location. So nothing special in this. It is a bit banging IIC. You can use this routines to implement your FTM chip I2C. So only the change you have to do in this definitions according to your port arrangements, and also we can have the trace is not important as well. Okay, so let's check with the FTM ID. So I already have this project open here. So to check what options I already set, so this is the name of the project, location I already set this chip, okay, 13X, and the compiler option is C, FMD CC. This is location of the exe. These are the compile options settings. Okay, so nothing special here. You just go through the build option. And we are placing the whatever the MC clear, and these are the some arrangement for the options. So according to your need you can place, but for right now I am keeping it as a default. So from some subscriber, he said that please give some I2C and SPI and UART routines for this FTM chip. So I am trying my best to start with I2C, then I will go with the SPI and the UART as well. So in this way you can build this. Please make a comment and please subscribe my channel. If you want this code, I can put on the Google Drive. Just ping the comment in comment box, and please subscribe and please support me. Thank you.